Okay, so what I want to do now is to introduce a way to think about geometry in the plane in a very, very, very precise way. So, first of all, imagine we want to describe our position on a line. So we describe a position on a line using numbers. So what do I mean by that? Well, when you learn about numbers, the first thing you learn about is kind of just counting whole numbers, 1, 2, 3, 4, 5. And then at some time you talk about the number 0, and then you talk about negative numbers, -1, -2, and -3. And when you're used to counting things, the concept of negative numbers is kind of confusing. But if you think about them kind of geometrically as sitting on a line, then you can think about them like kind of beads on a string if you want. And when you think about fractions and decimals and things like that, it kind of fills in every other position. So if you're thinking about a line like this going in this direction infinitely, then if I fix a scale, let's say 0 and 1, I can describe any position on this line using a number. For example, pi would be somewhere over here, minus 1.5 would be somewhere here. So this is a really brilliant thing because it allows us to think about a geometric object, like a line, using numbers, right? An arithmetic object. Okay, so what I want to do is to think about the plane, right? So that's where all of our geometry has been going on. Can we do something similar? So we can use this. We can use this to describe, if we're clever enough, to describe positions in a plane. So imagine I want to describe a position in a plane. So think about, for example, describing your position on the Earth. Now I know the Earth is a sphere, but let's pretend you're not thinking about the entire Earth, you're just thinking about a small piece of it, right? So the Earth looks flat if you're close up enough. So how do I describe a position? Well, one thing we can do is to kind of try to talk about how we kind of look relative to some sort of fixed frame, right? So what I could do is introduce two copies of the real numbers. So I'll call them, first of all, the x-axis. So horizontally, I'm going to draw the x-axis. So that would just allow me to think about ordinary numbers, positions on a line. But then I'm going to do something else. I'm going to take another copy of the number line, and I'm going to kind of lay it vertically. So I'm going to call this line the y-axis. So imagine I do this. So I've got my plane and I lay down these two axes. Now, can I use this to describe a position? Well, let's take a point, I don't know, let's say P. Is there a sensible way that I can describe this very concretely, just like I did with points in a number line? So I should say up here, this is called the number line. Called the number line. So notice, if I take a point P, there's a pretty natural way to extract two numbers. First of all, if I think about dropping a vertical line down, at the bottom here, I'm going to get some number on the x-axis. And I'm going to give this a name. I'm going to call this the abscissa. The abscissa of P. So it's kind of your measurement of how far you are or where you are in a horizontal sense. Similarly, I could move a horizontal line over here to give my kind of vertical position. So I call this B. And this, I'm going to give a name. I'm going to call this the ordinate of P. The ordinate of P. So if we think about it, if I know these two numbers, I know exactly where P is, right? If I give you the abscissa and the ordinate, it completely pins down the position of P. You can't have two different positions with the same abscissa and the same ordinate. So what I'm going to say is the following. I'm going to think about this position or describe it with a pair of numbers. I'm going to write A comma B, and I'm going to think about this in Cartesian coordinates. So this is a way of describing a position using two numbers. The Cartesian coordinates of a point are the numbers, or the pair of numbers, A comma B, right, where I think about this as my kind of the X, and I think about this as my Y, if you want, right? So the horizontal component and then the vertical component. So the point P isn't equal to that, not really. It's just described by that. So this is giving a way to describe a position in the plane once I've fixed two axes, an X and a Y. So this whole thing, once I've fixed two axes, is called something. It's called the XY plane. It's called the XY plane. Makes sense. It's a plane, it's kind of flat, but we've fixed an x-axis and a y-axis, which gives us this really concrete way of describing positions. So you may be looking at this and thinking, well, I've heard this before, but it's just been called coordinates. Why am I calling it Cartesian coordinates? Well, it's because it's named after the person who first introduced it, really. So yeah, maybe I'll show you what he looked like. It's me, there's more. Here we go. This guy. So this is the first person, this is the person who historically came up with this, this idea of using these two numbers to describe a position. Okay, and this is a man called René Descartes. René Descartes. Have I spelled that wrong? I think I have. So René Descartes, that's where the term Cartesian coordinates comes from. It's named after him. He was around a long time ago, as you can probably guess from the picture. I think he was around 1596, 1650, so hundreds of years ago. And I should say he came up with Cartesian coordinates. So it was introduced, this idea, in, I think it was 1637. I think it's kind of a really natural thing to think about, right? How do you describe a position in a plane? This is a really kind of clever way of doing it. And I think you've probably seen this before. Like, for example, if you've ever used a map or something like that, right? And you've had to describe a position on a map, you normally do it with kind of coordinates, and the coordinates are your horizontal and your vertical. So you've probably seen something like this before. So it probably feels really, really obvious. But back then, people didn't think about things with the same level of mathematical sophistication, and this was a really new idea, right? The idea of kind of thinking about something geometric with numbers in this very precise way. So it's actually really interesting when it comes down to it, the idea that people didn't really think like this until, well, the 1600s, which does feel like an awful long time ago, but do bear in mind that there were a lot of people doing mathematics a long time before that. Okay, so let's just do a quick example, shall we? So on graph paper, so I want you to do this. On graph paper, draw an x-axis and a y-axis. So you need to do that to use Cartesian coordinates, right? Now mark the positions . Now mark the positions, let's say 2, 3, minus 1, 4, minus 2, minus 2, 1, minus 3. So why don't you pause the video and take the time to do this, okay? Okay, so let me try this myself. So, graph paper is useful, right? Because it makes doing this pretty sensible. Let's kind of draw an x and a y axis. So I'll really do it overboard. So this is the x-axis, this is the y-axis. It's good to label them. So now let's go through each position. 2, 3. So 2 up to 3, So that would correspond to this. And I'm just going to write this as 2, 3. Okay, that's shorthand for that notation, that position. -1, 4, -1, up to 4. So that's this position. Right, so next, -2, -2. -2, -2 is here. And finally, 1 minus 3 is down here. All right. So first and foremost, with Cartesian coordinates, it's just a way to describe a position in the plane. Now, you can use them to do very fancy things, we'll see later on, but first and foremost, it's about describing positions very concretely. So let's take a moment to look at this picture. I mean, once I've fixed an x and a y axis, I can see here it's dividing my plane into kind of 4 pieces, right? These kind of 4 bits here. So let's label those pieces. So if I fixing an x-axis and a y-axis, divides the plane into 4 quadrants, I'm going to call them. Quad is 4, I think in Greek or Latin, one of the two. Into 4 quadrants. Fancy terminology. So it's a bit arbitrary what I'm going to describe now, because you might guess something different. But here's how it works. So this is my x and this is my y. So I'm going to call this quadrant 1, which is a bit surprising, because you might think quadrant 1 should be kind of here if you were used to kind of reading, right? So I think one would guess that quadrant 1 would be there, 2 would be there, 3 would be there, and 4 would be there. Okay, that's actually not how it goes. It's different. Instead, quadrant 1 is here. And really, it's because quadrant 1 is the most used when it comes down to things, because very often you have situations where both x and y are positive. So this corresponds to x greater than 0, y greater than 0. So it's kind of the most useful one, right? It's the one that turns up a lot when you're dealing with positive numbers. That's the reason it's the most was labelled first. Quadrant 2 is over here. And this corresponds to what? Well, x is negative over here, y is still positive. Then quadrant 3 is down here. A bit surprising again, maybe. Now this corresponds to both x and y negative. And quadrant 4, do it in Roman numerals. Quadrant 4 is, well, x is positive but y is negative. So it's kind of weird that's how it works. It just does, right? It's kind of a choice we make. Something we're going to see a little bit later on is there are other ways to describe your position in the plane. And what I mean by that is there are other kind of coordinate systems. One of them is called polar coordinates. And in polar coordinates, we're going to basically do something kind of clever. We're going to take the x-axis and think about rotating around it anti-clockwise. Strange that it's anti-clockwise, but that's what we'll do. And when we do that, we'll go through the first quadrant first, then the second, then the third, and the fourth. So when we look at polar coordinates, which is going to be a bit of an extension from what we do in the textbook, but I want to kind of show it to you because it's cool, we're going to see why 1, 2, 3, and 4 are kind of quite natural. Okay, so one of the best things about Cartesian coordinates is it gives us a way to describe geometric shapes in very precise terms. So Cartesian coordinates allow us to describe geometric figures very precisely. very precisely. So let's do an example. So example, so go to your workbook, L182, questions 2 and 3. So I want you to pause the video, go to your workbook and try doing this. Okay. So, question 2 and 3. Let's do question 2, shall we? So on a square grid, draw Cartesian coordinates. In Cartesian coordinates, mark these points and find the area of the corresponding shape. Okay, so let's do this. So let me take some graph paper and let's graph a y-axis and let's do an x-axis too. Okay, so let's mark the positions. The first is A, which is minus 4, 0. So minus 4, 0 is here. In fact, I'll do this in red. Next is B, which is 3, 0 over here. The next is C, which is 3, 4. Okay, that's up here. Okay, so this is A. This is B and this is C. And it's asking you to think about the area of the triangle given by linking these up. So we have very explicit description of this triangle, right? We know exactly where it sits in the XY plane. So it's a triangle. What's the area going to be? Well, the area is equal to what? Well, it's just equal to the base times height. So it's a half, or half the base times height. The base is 7. The height is 4. So this comes out to be equal to what? 14 square units. So in this case, we were given the vertices, right? So the corners of the triangle, exactly, very precisely in Cartesian coordinates. And from there we were able to solve, well, from there we were able to think about all the geometry we've learned to find the area. Okay, so let's do another one. Let's do question 3. So same basic story. But I think now it's going to be something a bit more, well, not much more interesting, but a little bit more interesting. So we've got X and Y. And we've got to mark all these positions. Okay, so minus 4, minus 4. Minus 4, minus 4. You get really good at doing this after a while. Next, 2 minus 4, so it's over here. Okay. To the same height, but a different position horizontally. 2, 2, up here. All right, and is it minus 4, 2? Okay. Brilliant. All right, so we've got to join these up. That seems to be what it wants us to do. And what do I get? Well, I get a square, thankfully. So the area, pretty simple, base times height. Base is 6, height is 6. So 6 times 6, which is 36 square units. Okay, so that seems like a reasonable place to stop. The overall moral of the story is Cartesian coordinates give us a way to describe positions in the plane very precisely once I fix an x and a y axis. They allow us to describe geometric shapes. We're going to see how we can think about kind of data using them. And we're going to see some other interesting things as well, which aren't necessarily in the textbook, but I want to show you because they're so cool. So I'll see you next week, okay?